Hello, everybody. So today we're going to be talking about the third and final of the individual gas laws, which is Gay-Lussac's law, which relates pressure to temperature. So we've seen these before, but we need to understand what our variables actually represent. So pressure, again, is the force being exerted by the gas molecules hitting the walls of their container. So like in the balloon that we see right here, right? The force that is making the balloon keep its size here is the gas molecules bouncing off and hitting the inside of the balloon. That is the air pressure inside. The more speed with which they hit the side of the container and the more frequently that they do so creates higher pressures. Temperature, we've talked about this, is the kinetic energy of the molecule or how fast the molecules are moving. So the higher the temperature, the faster the movement speed of the molecules inside the container. So Gay-Lussac's law relates, again, temperature to pressure. And as temperature increases, as we increase the kinetic energy of the molecules, that means they're moving around faster and with more energy. So the molecules move around faster, that means they hit the insides of their container more frequently. There's more collisions per second and with more force because they're moving faster. So not only are they hitting more often, but they're hitting harder as well. And this causes an increase in the amount of pressure that is being exerted on our container. And the opposite is also true, right? So as temperature decreases, the molecules move slower and with less energy, meaning they hit the containers inside less frequently and with less energy. So as temperature increases, the pressure also increases. And as temperature decreases, the pressure also decreases. This is similar to Charles's law in that they are directly proportional to each other, right? As temperature goes up, as we move to the right on our x-axis here, the pressure, our y-axis, also increases. And as temperature goes down, our pressure also goes down. So they are directly proportional to each other. So Gay-Lussac's law, because it's also directly proportional, looks a lot like Charles's law, right? Except instead of talking about volume, we're discussing pressure as related to temperature. So we have P1 over T1, or our initial pressure divided by our initial temperature, equals P2 divided by T2, which is our new pressure divided by our new temperature. And again, throughout this whole unit, we need to be using Kelvin as our temperature unit. If you use Celsius or Fahrenheit, again, it will not work properly. So I have another use for that simulation, that PhET simulation I showed you guys. So here we have a container, right? It has a set volume, the volume's not changing, and it has a pretty constant pressure of about 21-ish atmospheres, right? The molecules are moving around, they're hitting the sides of the container, and the pressure remains constant at a temperature of about 300 Kelvin. So we can adjust that temperature using our heating or cooling device right here. If we heat it up, you'll notice the molecules start to move faster and faster as the temperature increases, right? So now our molecules are moving much faster. Our temperature's gone up about 4 times as much as it was before, and our pressure has also increased a lot, right? We're now at 109 atmospheres of pressure and at a really, really high temperature here, and you can tell the molecules are moving around much more quickly. So if we do the opposite, if we cool it down, you'll see the temperature is decreasing. The molecules are moving slower and slower because that's what temperature is measuring. And the pressure also goes down, right? So the further we cool it, the slower the molecules are moving, the less frequently they're hitting the sides of our container, the less amount of energy they're hitting it with, meaning our pressure is going to decrease or be much lower than it was when the molecules were moving faster. So, as with all the gas laws, we see them all over the place. Pressure cookers, right, as we heat up the gas and the water inside in a set, it's a very strong container that's sealed, that increases the pressure, which is how pressure cookers work. They increase the pressure by heating it up, and then that in turn increases the boiling point of the water, so the food cooks faster because it's boiling at a higher temperature. Guns or any sort of propulsion mechanism like a cannon here, what's happening is you have the gunpowder, right, or the gunpowder or ignition source, and then when you light it, it really, really quickly produces some gas, but more importantly, heats up the gas that's in there super, super hot, really, really fast. And because of that, the pressure gets really, really high and shoves the cannonball or shoves the bullet down the barrel here and shoots it really, really fast. So the increase in temperature caused by the ignition causes a very quick increase in pressure. If anyone has used any sort of like aerosol or pressurized gas, if you pay attention, you'll notice that if you use a lot of it really quickly, the can starts to get cold, right? So if you go camping and use these propane containers here, it's a set propane container full of propane and you use it for your stoves. And if you use it for a long time, you'll notice that it starts to freeze at the bottom here. The water in the air starts to condense and eventually turn into ice on the bottom of our propane container here. And what's happening is we're using up the gas, so the pressure inside is going down very quickly. And as the pressure goes down, so does the temperature. And the temperature actually gets cold enough to freeze some of the water molecules in the air. This will happen if you ever clean your keyboard with like the canned air sort of stuff. If you spray that around, you'll notice that the can itself gets cold. And this is why you're decreasing the pressure inside, therefore the temperature goes down because they are directly proportional to each other. So I have a quick demo for you guys. You'll notice I am lighting a little receipt that I found on fire. I'm putting it in a container. It's burning, so it's making the air inside really hot, right? The air inside that Erlenmeyer flask is much hotter now. Then when I put the balloon on there, it deprives it of oxygen. And once the fire goes out, the air starts to cool. And so as the air cools, the pressure also goes down. The temperature goes down, so the pressure goes down. And now all of a sudden, the pressure outside of the container from the air is higher than the pressure inside the container. And so it pushes the balloon in through the flask here. You might have seen this trick with a boiled egg. Some people do it that way. I didn't want to boil an egg, so I just had a balloon. But again, as you decrease the temperature inside, it goes from really hot because of the fire, and then once the fire goes out, it cools down, so the temperature is going down, therefore the pressure inside the container goes down, and the air pressure from outside pushes the balloon into my Erlenmeyer flask here. So again, for the example problems, they're all very similar. You just have to know which equation to use. So we have Gay-Lussac's law right here. And so our example problem says a rigid container is filled with air to a pressure of 3.50 atmospheres on a cool day of 15 degrees Celsius. That's a little under 60 Fahrenheit. The maximum pressure the container can hold is 4 atmospheres before it will burst. So the next day, the weather heats up to 38 degrees, which is really hot. It's about 100 degrees Fahrenheit. We want to know, will the container burst? Will it explode? Or will it be able to withstand the increase in pressure? We know the pressure is going to go up because our temperature is going up, but we need to figure out what the new pressure will be. So first off, start with our initial data on the left-hand side. P1, our initial pressure, is going to be 3.50 atmospheres. And then on a cool day, so our initial temperature, our T1, is 15 degrees Celsius. So we have our P1, we have our T1, but again, we need to keep in mind that you cannot use Celsius for these calculations. We need to use Kelvin. So you just add 273 to the 15. So you end up with our P1 being 3.5 atmospheres. Our T1 is 15 Celsius, but we need Kelvin, so we do 15 plus 273, giving us 288 Kelvin. That's going to be our T1 for the sake of this equation. So Now for the right-hand side, it says the maximum pressure is 4 atm. That's not the pressure that we're going to have. That's just the maximum pressure we need to keep in mind. It says the next day, the weather heats up to 38 degrees Celsius. So that's going to be our T2. Will the container explode? So we need to, using our new temperature, figure out what P2 will be, and then see if it's greater than or less than our limit of 4 atmospheres. So P2 is going to be our variable. This is what we're solving for. T2, oops, this should be a 2 here. T2, our new temperature, is 38 degrees Celsius, and then we need it in Kelvin, so 38 plus 273 gives us 311 Kelvin here. So this is our T2. Then we just plug it into our equation. So we'd have 350 atm, our P1 divided by our T1 of 288 Kelvin, equals our P2, which we don't know, that's our variable, divided by our T2 of 311 Kelvin. Now, to get P2 by itself, in order to solve this, it's just a little bit of algebra. You multiply by the number on the bottom. Since we're dividing by 311, you do the opposite and multiply by 311. Then you end up with P2 by itself equals 311 times 350 atmospheres, or 3.50 atmospheres, divided by 288 Kelvin. Plug this into your calculator, you get 3.78 atmospheres. So that would be our new pressure of the container after it's been heated up by the sun. So the question asks whether the container will explode. We know that the maximum pressure it can hold is 4 atmospheres. Our new pressure does not exceed our limit of 4. Therefore, the container will not burst.